because actually it's some kind of the conductor on the edge and the bulk as an insulator. So the topological insulator anyway still a conductor on the surface there. Yeah, actually the topological insulator comes from the contribution of the Professor Ching-Ray Chang and also Molenkamp. And I visited his lab. I was quite impressed actually on all his impressed. And they together actually got the recently the fundamental physics prize. This is a photo actually for Ching-Ray Chang to get the prize. Okay. Okay, so before jamming needle resistance was discovered, the magnetic people never studied the transport behavior. They only care about localized moment. So the spin in order to face for the exchange coupling, but they only care about the localized moment. But 1988, they opened a window. Actually, jamming needle resistance is that the transport property actually among the magnetic spin electron. So a lot of material on the Fermi surface, up electron and down electron provide the spintronics magnetic. So in the very beginning, we call magneto-electronic or spin electronic, but later on they all merge together called the spin electron, spintronic, and there is a spin electron transport. But nowadays they move very fast to a different technology. Actually, they just as I mentioned, we not only provide the source, transfer the spin electron, but also we try to measure it now. So the spintronic is not only the charge, but also the spin. And we try to spin the water in this century. And the characteristic actually is that we need to have the spin carrier and long enough log time for you to measure things. So actually type of spintronic right now have a lot of different variety actually in the different material and also device. First is ferromagnetic base, giant activities, and also the spin transfer within semiconductor is logic circuit, spin state, the qubit, and the spin current. But no matter which one, the main issue right now is that how to create a spin current, transfer it, and most of all, how to measure it. So what is the difference between the charge current and the spin current? Actually, the charge current is each electron, they all carry spin. But during the charge current, all the spin actually is random. So in average, you don't see the spin. So you only observe the charge current. But for the spin polar current, is that you have a more up spin of electron than the down spin of electron. So you have the charge current together with the spin current. But the most weird thing is that we have the spin current, which means we have the up electron move in one direction, down electron move in the other direction. So actually the charge actually cancel to each other because the equal number of the electron go one direction. The equal number move the other direction. So charge current disappear, but you have the pure spin current. So what is the spin current actually? Except the charge, spin can be either up or down. So if you have the pure spin current, you will see your charge current, because these two move in the opposite direction. So total charge current is 0, but you have the spin current is not 0. So right now, we really have these 4 kind of things combination. You have pure charge current, because randomize our spin. And you have the up electron, down electron actually move in the same direction. And you also spin polarized current. You have more up electron and then down electron move in the other direction. You also have but this one you have the charge and the spin current together. And another possibility is that you have the fully polarized current move in the same direction and something like that. And the later on you have one side of electron spin in this direction, and for this one you have no charge current, but only have the spin current. And the first device was proposed by Dr. Doss. Actually, he said, okay, if I have 2D electron gas, we have ferromagnetic electrode here, ferromagnetic electrode here. if we can eject the spin from the ferromagnetic electrode, so because of the spin polar electron goes from here to the tertiary electron gas, then move to the other one, and you can detect here. So you can use the gate voltage to control the effective field in here. So the spin will experience the effective B field from the different voltage from the gate voltage. So Dr. Das proposed this idea. If you change the gate voltage, then you can rotate the spin actually when you transport in here. And then you change the gate voltage, increase the gate voltage, then you get it. And because actually when he come to here, he got a different orientation, so you got less output voltage actually from here. So you can use this idea to make an effect. And because you only rotate the spin, is not you don't consume the energy. It's not like the charge effect. It is called spin effect. And he proposed this idea. It's a good idea, but it's never achieved. Right now, main reason is that the idea he proposed of the spin current source is not a good one, because impedance mismatch and a lot of things happen in the interface. So make these things is not realistic. The second thing is, things just like the spin transporter. Actually, Spintronics proposed this. If you eject the current from here, because they polarize by the magnetic electrode, so it goes into here. But when during the conductor actually insulator actually they be polarized. So but when he hit the free layer, when he cancels out the the incoming ones, the electron in this way, outgoing one like this way. The spin torque, they have a difference for the in and out. So conservation of the torque, they must left over for this one. So they will change a little bit. So if you have flux, the current density of the spin electron like this way. So as long as the current density is strong enough, you can change the direction of the free layer. So this idea, which means we used to use the internal field to switch this one. So NR ratio is like this. But right now we can use the current to inject. And as long as the current density is large enough, you can switch this one. So that's the observation of this phenomenon. And turn out to be right now, people use this idea to do a lot of different things, such as the spin torque narrow oscillator actually also use this idea. And later on, people realize that we even can use this idea within a single ferromagnetic metal, such as you have domain structure actually in a magnetic metal. So if you eject the current like this way, and during domain war, they also do like that. So they can move the domain war, not by the external magnetic field, also by the current, you can do that. And this was observed actually quite a lot. And Stuart Barkin used this idea. I think they proposed the rest track to storage the information into the three-dimensional things. That's for the spin torque to transfer the things. And later on is that can we provide the spin current? How we do that? The Dr. Das idea, you need a good spin source. And this is something like the battery. You have the charge battery, and you have a spin battery, provide the spin current. You use the charge battery. And so what is the spin pumping? Actually, the first idea is just a reciprocal of the spin transfer torque. Actually, spin transfer torque is that you use the spin polarized current, switch the local moment. And this one actually, the first idea is use the ferromagnetic reference. If your microwave cancels out, you reference the local moment. And the local moment reference, and later on, because you keep going, eject the angular momentum from the microwave, then this one, the only way for them maintain the ferromagnetic resonance, they need to send out the spin current. And so they pass out the angular momentum through the spin current. So this is somehow the first way to propose actually this idea. The basic idea, if you see from the rotation branch, then it's become very clear. for the lab coordinator, you see the kinetic turn and also your rotation, field actually interact with your spin. And this is rotation. And so if you use the unitary rotation operator, you can change the lab coordinate to the rotation frame. And in the rotation frame, you will get your result is similar like what you have the lab frame, but you have another Zeeman splitting because you go to the rotation frame. And so your price actually go to the rotation frame is that actually you introduce somehow the Zeeman splitting or up and down electron by this splitting actually depends on rotation frequency. So actually, so the price you paid actually is you double in the terminal, which means in the lab frame actually you see like this, the ferromagnetic resonance. But in the rotation frame, you see this one doesn't move. But however, other things, and you will see the Zeeman splitting up and down in the other side. So if you go to see the spin pumping things like here, so if you have the sample was doing the spin pumping during the rotation frame, and you will see actually your lead, the up electron and down the electron will have the spin splitting, Zeeman splitting, and then so you will see up electron goes to here, down electron go to here, so you have spin current cancel out. And also similar things, you have the other side. Oh, sorry. You also have the other side that has the similar things. So because of symmetry, your spin current move, left and outside from the spin pumping. So actually people do use this one right now as a spin source. If you contact the magnetic material on the platinum, you do the ferromagnetic resonance, and then you will see spin current pumping, And because platinum is heavy metal, so they have large spin orbital interaction. So you can observe spin current go this way. You will from the inverse spin Hall effect, you will observe the current actually flowing in the other way. So actually, if you have spin current this way, you always have a charge current induced for the largest spin orbital interaction material inside. So spin Hall current is if you have electric field drive your charge current in here, and if you have spin orbital interaction, then you have a charge the spin current will go to the orthogonal direction, and like this way. That is we call the spin Hall current. And the explanation is a spin orbital interaction. The spin and the orbital will interact with each other. So actually, up electron they will move, and the down electron move in the other way. So you have net spin current actually go this way. So spin Hall effect actually can be also a source of the spin current. Right now, actually, people are doing something like that. If you the reverse things like the ferromagnetic resonance, they eject the charge current. Right now, they use on the titanium and the platinum. They eject charge current in here, and so because of the charge current go this way, spin Hall effect, they will accumulate on top and the bottom. So the spin current go to the ferromagnetic things, and they also put the junction device in here. They realize right now they can use this spin current to switch the free layer. Very effective, and also much effective, in this way. Actually, this is just a new paper published in Science in last year. In Python, actually, they eject the current, and the spin current goes into the copper ion boron. They can switch that. They can observe these things. But this is so right now they have a lot of things proposed. All logic device comes up based on this very effective spin current source. Is that conventional CMOS logic is that you use the charge on the capacitor to do the MOS. Right now we use the charge current to transfer, and right now we use the pure spin current to transfer the things, and they use the state of magnet as a information. So you can propose all spin logic, and quite a lot of group right now working on these things right now. If this one can be realized, then we can replace the CMOS. That's a big issue, and because the spin current doesn't cost energy, so it's very energy conservation industry. And also, so similar things, you have the inverse spin Hall effect. Because you have the charge current, you have spin current in here, and the up electron and down electron will move in different way. So you have the spin Hall effect. But if you have the inverse spin Hall effect, if you have inject the spin current in this way, because of spin orbital interaction, your up electron will move in this way, down electron move in this way. So you have the net charge current will go like this way. So this we call the inverse spin Hall effect. So right now people also use the inverse spin Hall effect to measure the spin current, because you can use the inverse spin Hall effect to convert the spin current into the charge current. So actually, we can use this way to measure what is the spin current. Because actually used to be we can use the optical way and the electrical way. Optical way is a magneto-optical rotation. And we also use the spin Hall effect, such as this. You have two magnetic stripes in here. So you have spin Hall effect, and you connect on the different, you change the magnetization on the magnetic stripe. So you can use spin Hall effect to measure the spin current. And you also can use the inverse spin Hall effect to measure that. But however, we still don't have any effective way. We always convert the things to the optical signal, electric signal to measure spin current. We still doesn't have a direct way to measure spin current. Maybe if in the future we can have a direct way to measure spin current, I think the whole thing application will change again. Okay, I think that is the things. I want to go back to some kind of history. That's a general introduction. And if you go back to see let's say initial paper actually by Peter Grunberg, they found the antiferromagnetic coupling on the ion layer among the chromium interspacer. And this paper actually was quite a heavy citation right now. And the antiferromagnetic coupling actually is something like this. If you have up electron, you magnetize this in one way, and this is in the different way. And the conduction electron in between that, where because of the Fermi wave vector, they will have the oscillation something like in here. So if you change the thickness of the spacer, they will oscillate like RKKY oscillation, something like that. And Albert Furth actually used a four-point detector. He measured that. So if you apply a large field in this direction, and you will saturate altogether, he chose a spacer to make if you don't apply any magnetic field, they are antiferromagnetic coupled. So you have a large right field direction, and they orientate this way. And he identified the magnetic resistance will drop when they are all in the same direction. But they are larger in the antiferromagnetic arrangement. And also this is isotropic. And at that time when he got this one, he realized this is not a conventional Lorentz magnetoresistance as observed in all the material, also not an anisotropic magnetoresistance. So he named as a John magnetoresistance, published this paper in the Physical Review letter. The basic idea is that actually up electron, if you lay same direction, they are less scattering, they can go smoothly. If you have the opposite down electron goes in the this magnetic layer in the up orientation, they will scatter much easier. So if you use a circuit idea, it's something like you have the how do you say that? Very small resistor in series, large resistor in series. Then they in parallel, arranged in parallel. So you can calculate the effective resistor from the circuit series. And this one can be easily calculated on something like that. When the two magnetic layers are in parallel, their effective magnetic resistance should be like this way. However, when you have antiferromagnetic arrangement, so up electron less scattering, but heavy scattering in this way. Down electron heavy scattering and less scattering. So you have large resistor and small resistor in series. And also your small resistor and large resistor in series. Then put these two circuits in parallel. So you can have an effective resistance and antiferromagnetic arrangement. and you got actually the effectiveness is like this way. So the difference is NR ratio is always like this. So it's very easy from this simple picture is that if you want to have a large geomagnetic resistance, your up electron and down electron need to behave very different. And also the spin electron need to be maintained within this spacer. So spacer thickness cannot be very thin. Cannot be very thick, otherwise because of scattering, they will forget their spin orientation. So this will be thin enough, and also the electron need up and down need to be very different. Then you can have a large geomagnetic resistance effect. Why this effect was never observed before, but only recently, in 1980. If you take a look at basically fundamental solid state theory, you know your lambda actually character wavelength actually is related to your Fermi wave vector, and the Fermi wave vector actually is some kind of depends on the cubic root of the carrier concentration. For the metal, actually, usually the carrier concentration is cubic centimeter is you have 10 to the 2012. So if you use this formula to estimate, it's 0.1 nanometer. It's 1 angstrom. And the semiconductor is about 10 nanometer. So this one, quantum behavior of semiconductor is easy to observe, but for metal it's not non-trivial. So you can see, unless your technology can control very precisely on the angstrom range, you cannot see the behavior. But semiconductor is much easier. So semiconductor behavior. So why spintronic can solve? Because spintronic exchange, we have one very important character length. It's called exchange length, usually proportional to the wall length. It's also about 1 to the 10 nanometer. So only when your technology goes down to this way, you will observe the spintronic phenomena. So later on, people also identify why don't change the conductor into the insulator, and turns out to be spin-dependent tunneling also can give you the large tunneling resistance. If your tunneling is spin-dependent, so you have majority and minority. This is very simple model from the Julia model. He published this paper with 2 pages on the physics letter. 1 page experiment, 1 page is the theory. And the basic idea is that you have majority and the minority, up spin, down spin. And if you are in the parallel state, the majority is the same. If you have anti-parallel state, the minority will be here, become majority. So in parallel state, your tunneling is proportional to the majority to majority, minority to minority. And conductance, your anti-parallel is the majority to minority, minority to majority, so like this way. So difference will give you this. Polarization is defined by the majority and the minority difference. So that's the polarization of the magnetic material. So actually the tunnel magnetic resistance is proportional to this. And Julia published paper actually back to 1975. However, it's quite interesting. This paper nobody cite. Nobody read before 1987. Citation 0. So if you publish paper, nobody cite, don't be frustrated. 75 to 83, quite a long time. Nobody cite at all. Turned out to be 1983, only 1 citation. 88, another one. But after that, 1990, 1160. So it's like booming, So if nobody cited your paper, you need to have confidence on your work. But at that time, people used the aluminum oxide as a barrier. It's follow the Julius model. However, later on, people identify if you use the NGO as a barrier, then suddenly you see still the slope like the aluminum oxide gradually increase, hard working, but suddenly when NGO introduced, they just jump like crazy. It's a different. This was proposed by the series, band calculation series, and later on was realized by Stuart Parkin and also Japanese colleague actually, right now actually Tohoku University pushed that to the 500, or 600 right now. And this application in magnetic recording is quite important actually, because spin bar, this is spin bar structure, entanglement layer, and the exchange coupling, the pinning layer, and then the free layer. And this idea, free layer you don't need to care about thickness of spacer, so you can pin it this free. And used to be, the magnetic recording head is used the Faraday law, so you need to rotate very fast, because it's the flux rate change give you the voltage, the signal. But right now, if you use the NR sensor, they are much sensitive than the flux rate change. Also, you don't need to rotate very fast, because they only change the orientation, give you the signal. And right now the rotation is very fast, just for data transfer rate. It's not for the signal output. This is the very interesting figure. It's really for the Dow Jones, Dow Jones, the stock market. Actually, as I mentioned, I was a major actually is in this field. So when I graduated, I almost joined this company. This company on the 1985 to 95 is the largest worldwide company on the reading head company. Their home base is Santa Barbara. I was interviewed over there for 3 days. I was a poor student at that time. I still remember. Their VP, buy me a dinner in the beach of the Santa Barbara. They opened a red wine, $200. I was shocked, really at that dinner, because I probably spent $20 for my whole week. And he opened a red wine, and for $200, I said, this is a good company. But anyway, this company, if you see, because they are, the largest reading head company. On the 1996, actually IBM proposed the prototype of the jamming resisting head. And this company have a lot of cash, and the dominant company, they say it's impossible, no one can replace me. So they don't trust that. But after IBM announced the real product, use the jamming resistant head, they drop down, then come back, then drop down, within, how many years? 4 years. From $60 to 3 cents. To 3 cents. So they out of the market. So new technology is really killing technology. This is the demonstration of Spintronics. So people believe that. So that's the reason why they keep pumping the money into the research. So later on, they proposed actually, it's not possible to do magnetic random access memory. We call NRAM. What is the benefit for the magnetic random access memory? Because it's non-volatile. Right now, we use the DRAM. Hard disk is non-volatile, but DRAM actually is volatile. So every time when you turn on your PC, you wait for a long time. Why? They boot the operating system from the hard disk into DRAM. Because you turn off the things, everything evaporates. So if you have the non-volatile RAM cheap enough, then all the PC will replace by this. So you don't need a hard disk. You turn on your PC, immediately on. Sometimes, actually sometimes you go to your laboratory or office, you turn on your PC or workstation, you never turn them off, because Microsoft. You turn on the machine, Microsoft writes so complicated software. Took about 5 minutes to turn it on. Took about another 5 minutes to turn it off. So make you think you don't want to turn them off. So you waste a lot of energy. So if you have the immediate on, instant on machine, you can always turn them on and off. So this is quite a green technology right now. But still, it's already on the market, but too expensive now. A lot of reasons for that. Okay, I think